Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we are going to do two different things. We're going to look at reviewing what we know about acids and bases already, including naming and some basic properties and how to recognize them. And then we're going to move forward and we're going to look at three different theories about acids and bases. And kind of how the theory of what an acid and base is has evolved. But the first thing we should do is we should do a quick review of how to name acids. Now, how you name an acid is really dictated by the ending of the anion in that acid, whether it's an "ide" or an "ate" or an "ite." So, for instance, if I had something like HF aqueous, its ionic name would simply be hydrogen fluoride. It has an IDE ending to the name, but when hydrogen fluoride is dissolved in water, it will react with water at least somewhat to form acid. So in this current state of aqueous hydrogen fluoride, this has an acid name associated with it because it has now formed acid in solution. Now, when I have an IDE ending, what the rule is the name becomes hydro, then the root of the name, ic acid. So the hydrogen becomes the hydro, and the ide becomes the ic, and then the root of the name goes into the blank spot. So this would be hydrofluoric acid. So again, the rule for naming an acid with the anion ending with "ide" is hydroic acid. Many anions end with an ending "ate" or "ite". Those are generally falling underneath the polyatomic ion chart. And when a hydrogen "ate" anion or a hydrogen "ite" anion get dissolved in water, they generally form an acid. For example, something like H2CO3 as an ionic name would be called hydrogen carbonate. Now, when dissolved in water, it's going to form carbonic acid. But how I come up with that name really comes from this ATE ending. An ATE ending turns into the root of the name ic acid with no hydro in front. So this would be gone, the hydrogen part of it, and the root really comes from here, the carbon part of it. So this name would be carbonic acid. Anything that ends with "ate" becomes blank ic acid. Off to our last naming rule. If you end with an "ite", then your ending as an acid name becomes us acid. So for instance, if I had something like HNO2 aqueous, as an ionic name, it would be hydrogen nitrite, and it ends with that ITE ending. Anything that ends with "ite" becomes blank us acid. So for instance, the hydrogen would also be gone. It's not hydro something us acid. That's gone. This is simply going to be nitrous acid. And there's our three naming rules for acids. What I'd like you to do at this time is to complete the following table. Now, I haven't discussed the IUPAC acid name in detail, so I am going to help you there. The IUPAC acid name always starts with the word aqueous, which simply means dissolved in water. So this would be aqueous, 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 and then followed by its standard ionic name, which I've been using in the examples above. So for instance, HCl would be aqueous hydrogen chloride, and ClO4 is called perchlorate, so this would be aqueous hydrogen perchlorate. The common name is when we change the "ide" or the "ate" or the "ite" into a hydroic, ic, or us acid. So the common name for HCl would be hydro, root of the name, chlor, suffix ic acid. Please pause the video at this time and try to complete the rest of the table. Now that you've had a chance to do that, let's complete all the IUPAC acid naming systems. Now, the IUPAC naming system is kind of easier than the common naming system, but the common naming system has been around for so long that most people just use the common naming system when talking about acids. So as I continue down this chart, everything has hydrogen, so it's always going to be aqueous hydrogen, aqueous hydrogen, aqueous hydrogen. Then I have to look up the anion, which is a polyatomic. So ClO3 is chlorate, ClO2 is chlorite, and ClO or OCl, which is the exact same thing, is called hypochlorite. Now what you'll notice is I have two eights. I have perchlorate and chlorate, and I have two ites, chlorite and hypochlorite. The eights both have to follow the 8 rule, which is to become ic acid, and the ites both have to follow the ites rule, which ends with us acid. The only difference you have to remember here is the term per or the term hypo, which indicates how many oxygens the anion has. So this is just as a side note. This isn't something that we really have to take in at this time. But whenever you have an 8, like chlorate, if you add an oxygen to it and it becomes 4, this now gets the prefix per, saying that it's completely full, or I wouldn't want to say perfected, but a complete. Okay, that's the maximum amount of oxygens it can have. If you lose an oxygen, you get the ending of ite. And then if you lose yet another oxygen, it gets the prefix hypo. It still has the ite. So that was just a little side note how you can actually figure out whether something is a per or a hypo or an ite or an ate. Let's do the actual naming. So for both of the 8s, it's going to end as ic acid, and for both of the ites, it's going to end as us acid. And now all we have to do is put the root of the name in there. So the first one would simply be perchloric acid. Then we will have chloric acid. Then we will have chlorous acid. And then we would have hypochlorous acid. The next thing we're going to look at in today's lesson is a review of acid and base properties that should have been developed over the last number of years. So very basic understandings of what acids and bases are. So probably starting with the most important point is, what is acid? So to you should know that acid is a hydrogen ion. And we are going to learn today that it is actually a hydronium ion in solution. So hydrogen ion or hydronium ion. How much you have of hydrogen ion or hydronium ion dictates what your pH will be and how acidic a solution is. The other thing that you should know for sure is that the pH must be less than 7, or I often say pH is below 7. Now realistically, we usually say 6 to 8 is neutral, but by definition, below 7 is acidic. The next thing you should know is that they always conduct electricity. And the more ions in solutions, the better it conducts. The next thing we should also know is that they taste sour. Next, we should know that they turn litmus red. So when it comes to red litmus and blue litmus, they turn litmus red. Now the way I always remember this is acid ends with a D and red ends with a D. So litmus turns red. So for instance, blue litmus will turn red and red litmus will stay red. Acids can also be corrosive. It depends on the acid, it depends on the metal in terms of the corrosive nature, but also it can be corrosive to biological material as well. In terms of bases, I'm going to do something very similar. So number one, what is base? Base is a hydroxide ion in solution, so that has to be aqueous. The pH has to be greater than 7. Realistically, we would probably say greater than 8. I often write it as pH would be above 7. They too will also conduct electricity because there are ions, hydroxide ions and other ions, so this will conduct electricity. 4, they taste bitter. If you've ever had your mouth washed out with soap, soap is a base and it tastes very bitter. If you haven't had your mouth washed out with soap, just give it a try. All right, the litmus will turn blue. The way that I always remember this is base starts with a B and blue starts with a B. So to be clear, blue litmus will stay blue and red litmus will turn blue. Now bases can also be corrosive, not to metals though. They are corrosive to biological material. So pouring a strong base on your hand and leaving it there, or pouring a strong acid on your hand and leaving there, has a very similar result. It will kill the skin. Bases though, you don't feel it as much. It's because bases feel slippery, it doesn't feel so much like burning when it first starts to react with your hand or whatever it might be. A good example of a base used in a household would be something like Drano. So Drano is used to clear clogs, and it is a very, very strong base. And it is just as damaging to human skin, biological material, as a strong acid would. So the next thing we're going to look at is how did we recognize something was an acid or a base at a lower level of chemistry than we are currently at? And generally you would have been told something along these lines. You will have a hydrogen that will appear one or more times on the left-hand side of the formula of an acid. And of course, this would also have to be aqueous. So for instance, there is HCl gas, that's hydrogen chloride gas. It's not an acid yet because it hasn't released its hydrogen ion in solution. So that isn't an acid. But of course, if I had something like HCl aqueous, that is hydrochloric acid, that it is an acid. So, I mean, examples would include things like HCl, which would be a strong acid, aqueous, or HF, which is a weak acid. These are both called monoatomic because they have one hydrogen ion. We're going to talk about monoatomic and diatomic at a later point, but I'm going to mention it now. Or maybe you had something like H2SO4. This is a diatomic strong acid because it has two hydrogens. Or maybe H2CO3 aqueous, which is carbonic acid, which we just learned how to name. This is a diatomic weak acid. Or even something like H3PO4 aqueous, which is called a triprotic acid. It is also weak, but it is a very strong weak acid, if that makes sense. The other thing that you probably would have been taught is you're looking for a COOH group. This is called a carboxyl group, which is part of organic chemistry. And carboxyl groups make carboxylic acids. And you probably wouldn't have dived too far into this. You probably would have been asked to memorize something like vinegar, which is ethanoic acid, also called vinegar, or acetic acid. It has a COOH. This H here is the one that turns into hydrogen ion or hydronium ion. Okay, and we're going to get into that more. The other one you may have come across is oxalic acid, which is HOOCCOOH. And again, it has two of these COOH groups. So this has COOH, but this also has a COOH there and a COOH here. So this is a diprotic organic acid. This H would turn into an H plus or hydronium. This one also could. Now, a common question I always get at this point is, why do they write it as COOH? Okay, so we don't really need to know it quite yet, but a COOH group looks like this. And the fact that you write it as COOH tells the person reading it that it has this look to it. This is how it's structured. And the reason why it loses this H is because of the extreme polarity of that bond. This is extremely negative, this is extremely positive, and essentially this hydrogen can leave underneath the right circumstances. Again, we're going to get to that later today. The next thing you would have looked at is, well, how do I recognize something is basic? Now, what you'll notice is I never did a review of basic names because they are generally just ionic compounds or molecular compounds that follow their standard naming system. So the ones that everybody probably be the most comfortable with would be a group 1 metal cation. So something like Li plus, Na plus, K plus with a hydroxide ion, so OH minus. So that would make things like lithium hydroxide aqueous or sodium hydroxide aqueous. These are probably the most popular common bases, and these are all strong bases. Essentially, they are 100% soluble in water to produce hydroxide ion, and hydroxide ion is basic. Now, you can have lots of things like copper hydroxide, etc. Those are very insoluble in water, although they will dissolve a little bit and produce a little bit of base. We generally kind of stay away from those. We stick with things that are highly soluble, so group 1 metal cations with OH minus. There are a couple of group 2 that are highly soluble but are not considered soluble in our data book. Things like strontium 2 plus is actually fairly soluble with hydroxide, as well as barium 2 plus is fairly highly soluble with hydroxide. However, it does not meet the criteria of 0.1 moles per liter dissolving, 0.1 moles dissolving in 1 liter of solution. The other one that was probably mentioned to you is ammonia, not ammonium. Ammonia is NH3. Ammonium is NH4 plus. This would have to be aqueous, and probably no explanation was given, and I'm not going to give an explanation at this time, but later in the video when we look at different types of theories. This would be a molecular base, but I can assure you there are many more molecular bases out there, and there are many, many, many more bases that are ionic that are out there that we will learn over the next few lessons. We are now going to look at the first of 3 different theories on acids and bases. The first 2 were all brought forward by somebody named Arrhenius, and he made his original theory and then modified it. So we're going to look at those 2 theories first. So the original thought was that all acids would ionize to form hydrogen ions in aqueous solution. Now, this isn't really wrong, it's more kind of incomplete. So, for instance, if I had something like HCl gas and it dissolved in water, and it would because it's a polar molecule, it would ionize. Now, what the term ionize means is to turn into ions. So HCl itself as a molecule is covalently bonded and isn't technically ions. So in order for it to become ions, it would have to undergo ionization, in which electrons would be transferred from the hydrogen to the chlorine to make hydrogen ion and chloride ion. So it's called ionization because I took a molecular compound and I've turned it into ions. Then the thought is that hydrogen ion is acid. It was a very good first attempt, and it is kind of correct, but it's incomplete. Then the Arrhenius definition of a base was that it's a substance that dissociates to produce hydroxide ions, which is correct, but it is incomplete. It just doesn't cover all bases. So there's nothing wrong with that statement. It is a true statement. It just doesn't cover all bases. So for instance, KOH solid would dissolve in water because it's 100% soluble, and it dissociates. It doesn't ionize, it dissociates because it already is ions. The K is a cation, K+. The OH minus is an anion, OH minus. It doesn't need to ionize like an acid. It already is ions. It just needs to dissociate into its parts, which are K plus aqueous and OH minus aqueous. Of course, OH minus aqueous is base. That's what it is. In this next section, we're going to look at Arrhenius's modified theory. So this theory allowed for us to better understand what acid truly is, and also expanded how many things could be acidic. So the new definition says that acids react with water, not ionize in water, to produce hydronium, which is H3O+. This is called hydronium, in aqueous solution. So it's not ionize, it's react with water, and it's not H+, it's H3O+. Now, to be honest, we use H+ as acid a lot of times in chemistry. Just thinking of redox chemistry, we really don't use H3O+. However, acid really is hydronium, H3O+. Okay? So let's talk about what's actually happening here. So I've picked HI, which is a strong acid, which essentially means that this reaction goes to completion. It ionizes or reacts with water 100%. But I'm going to draw this out as kind of a bonding question almost. So I would have 3 lone pairs of electrons on it, and it would share 2 electrons with hydrogen, like this, in the valence shell. Water would look something like this, with its 2 hydrogens in a bent shape. Now, what essentially happens is when these things bump into each other in a solution, so we would have to bubble hydrogen iodide gas through water, it would dissolve because it's polar. The I would be the negative end, and the H would be the positive. And then it's going to bump into very polar water, oxygen being the negative end and the hydrogens being the positive end. And if they hit in just the right way, in the correct orientation, with enough energy, this hydrogen will actually leave the I and join the O here, piggybacking on these two electrons. It actually leaves its single electron behind. Now, during this motion of moving from Hi to OH, to water, I should say, it is a proton. It is H+. It is just a proton. That is all it is. So what ends up happening is the I is still there. It has all of those valence electrons, including the one left behind by hydrogen. So let's say this is the one that it was sharing with hydrogen. It still has that electron. That would make it negatively charged. Hence, I-. And then it's also going to produce hydronium. So now I have this hydrogen piggybacking on the two electrons on oxygen, and it's making this ion. Now, because it has gained an extra positive, the positive being the proton of hydrogen, this is now positively charged, and this is called H3O plus, or hydronium, which is acid. So this is what happens at the molecular level when a polar molecule containing hydrogen is dissolved in water. And in this case, because this is a strong acid, again, I'm going to talk about strong and weak in later on lessons, this is 100% forward. This happens all of the time when dealing with hydrogen iodide in water. So in Arrhenius's modified definition of a base, he did not go back on his original definition. He actually just added to it. So for instance, in the original definition, it said that bases dissociate to produce hydroxide ions in aqueous solution. But this didn't cover everything. It actually missed a huge amount of bases. So what he did is he added this extra piece. I'll explain it in a moment. He said bases dissociate or react with water to produce hydroxide ions. So what are these things that react with water to produce hydroxide ions? In general, they fall under two major categories: anions or molecules. So the first one I'm going to look at is an anion. An anion is something which is negatively charged. Now, basically, all anions will do this to some degree, other than the 5 neutral anions. So just as a quick review, the neutral ions in a neutral ionic compound would include 5 of the 6 conjugates of strong acids. So neutral ionic anions would be ClO4 minus perchlorate, nitrate, NO3 minus, iodide ion, chloride ion, and bromide ion. So these would be exceptions to this anion rule. These anions will always be neutral. I'm basically talking about all other anions. Now, if you're wondering, well, why would an anion be a base? Well, I'm going to show you this using Lewis dot diagrams again. So let's imagine we had fluoride ion. Now, normally fluorine would have 7 valence electrons, like this. However, as a fluoride ion, it would have an extra electron. That's the extra electron it gained to become negatively charged. Now, if this comes close to water, so let's say we had HOH like this, and if it bumps into that water with enough energy in the right orientation in just the right way, what can happen is it can tear this hydrogen away from water and attach it to these 2 electrons. So I'm going to do that one more time. If these hit into one another just with the right amount of energy in the right orientation, like when you meet the perfect somebody, it just happens, everything comes right just at the right moment. Okay, what it can actually do is drag this H away, leaving these electrons behind. It's not taking these electrons. This hydrogen is essentially jumping ship and piggybacking on these two electrons to form an HF molecule. So let's show that. This would jump ship there as H+, which essentially is just a proton. It is a proton. And it would join HF. So what would that make? Well, that would make F H, which is this, HF. Now, this is a very polar molecule, so it will stay dissolved in water. And then what's left of my water? Well, what's left of my water is this. Well, that's OH. Now, the reason why it's negative is it has lost a positive. When it lost this hydrogen, the hydrogen is positive. So water in its current state is neutrally charged. It has no charge. But when it loses a proton, which is positive, it becomes negative. So now this is actually negatively charged because it has one more electron than proton. This is called hydroxide, and this is base. So in summary, the new definition just added this extra part which said bases can dissociate but actually or react with water. And the things that react with water are usually anions or very polar molecules such as ammonia, which I will use to explain the next definition we're going to do on acids and bases, which is Bronsted-Lowry. So I would like you to keep in mind, you've learned something massively new at this point in terms of bases. Bases are essentially going to be negatively charged anions with only a few exceptions, such as these ones up here. And there are some anions which can actually act as an acid if it has a hydrogen associated with it. Again, we're going to get to that a little bit later. I don't want to get too far ahead of myself. So for our third theory on acids and bases, we're going to look at the most accepted theory, which is called the Bronsted-Lowry theory of acids and bases. And I feel that it is the most complete theory and actually the easiest one to understand. Now, the Bronsted-Lowry theory is really taught in Chemistry 30, not 20. It's out of scope in 20. But because this is a precursor course, and because I feel it actually allows students to better understand acids and bases, I do teach it at this point. But I would never ask you what is a Bronsted-Lowry acid or what's a Bronsted-Lowry base. It's essentially for you to understand a topic at a deeper level, assuming that you will continue on in chemistry as well. Okay, so Bronsted-Lowry acids are called proton donors, and bases are called proton acceptors. That's it. An acid is something that donates a proton, and a base is something that accepts a proton. And if you're going, well, protons are found in the nucleus. What is he talking about here? Let me give you a little bit of background, okay? When you have a hydrogen atom has one electron, and it has one proton and no neutrons. This is a hydrogen atom. Now, if this hydrogen atom loses this electron by either leaving it behind or giving it away in some kind of way, what it would turn into is simply just a proton. This is H+. This is a hydrogen ion. But a hydrogen ion is a proton. That's all it is. Once it loses its one electron, a hydrogen atom just is a proton. So when we talked at the start of the lesson about H+ being acid, acid is a proton. That is what it is. It is this proton here. So Bronsted and Lowry came up with the same definition at the same time, and they essentially said acids are proton donors, which is a hydrogen ion, and bases are a proton acceptor. They accept a hydrogen ion. So let's look at another example here, and I'm going to just do the description in a slightly different way. So I'm going to stick with a strong acid because that's mostly what we deal with at this level. And I'm going to use something like HBr, aqueous. And it, of course, would still have to react with water. So H2O. Okay. So what would happen is the acid, this is the acid, would have to donate this H to water. So this H plus is donated to water. Now, I'm going to change this picture slightly. I'm going to make this a lone pair of electrons. Okay. These electrons here, which were shared between hydrogen and bromine, are left behind. They do not come with the hydrogen. The hydrogen itself is literally only a proton. It leaves these electrons behind. And then what it does is it piggybacks on a pair of lone pairs of electrons on water. So then it would become H3O, but because H2O has gained an H and a positive value, it's H3O plus. What remains of HBr now is Br minus aqueous, because it still has that extra electron making it negative. So this is still a reaction with water, which Arrhenius brought up in his theory, that acids have to react with water, which they are, and it is still producing hydronium, which is acid, but it talks about it in terms of a proton donation. Now looking at bases, bases are called proton acceptors. So if a proton is positive, something that accepts a proton would have to have the opposite charge, because we know positives don't like positives and negatives don't like negatives. So if something is going to accept a proton, it has to be negative in some kind of way. Well, what are some negative things in chemistry? Well, negative things in chemistry would include anions. Those are very negative. So when a hydrogen ion comes near it, it goes, well, I like negatives. I'll join up with you and we can form HX. The other thing it can be is a very polar molecule, because very polar molecules have a negative and positive end to them, and therefore they can almost act like an ion in a certain section. So I'm going to use the example of NH3 reacting with water, and I'm going to draw it out for you as well. So this would become NH4, because water would actually give up its hydrogen here to ammonia to become NH4 plus aqueous, and then all that's left of water is OH minus aqueous. So because the hydrogen is going to ammonia and ammonia is accepting the H plus, NH3 is considered a base. Now, I bet you some of you are asking yourself right now, well, water is donating a hydrogen here. Is water an acid? You bet it is. It is the most common acid and actually the most common base on Earth. Now, to clarify, water, pure water, is neutral. It's no acid, it's no base. It is neutral. But when you put it with something that can accept a hydrogen, it will act like an acid, like in this scenario. And if you put water with an acid, it'll accept a hydrogen and act like a base. So up here, water is actually accepting an H+, and by definition, that makes water in this scenario a base. Water can both accept hydrogens and donate hydrogens. And when something can do that, it's called amphiprotic. Amphiprotic is a term you don't need to know for Chemistry 20, but it's absolutely a term you need to know for Chemistry 30. An amphiprotic substance can act as an acid in certain scenarios, and it can act as a base in other scenarios. And if you're saying, well, what are those scenarios? I've just said it, and I'm going to repeat it. If I put water in with an acid, it will be forced to act like a base. If I put water in with a base, it'll be forced to act as an acid. And the analogy I always give is as a teacher. As a teacher, depending on which building I walk into, I could actually be a teacher or I could be a student. So based on law, if I walk into any elementary, junior high, or high school in Alberta, I automatically become a teacher, and I'm legally responsible to act as a teacher. I am forced to act as a teacher going into that type of school. But if I walk into a university, I am forced to be a student because I do not have a PhD and I cannot teach in a university setting. So it depends on where they are. If water is put into a base, it's forced to be an acid. If I'm put into a high school, I'm forced to be a teacher. If water is put into an acid, it's forced to be a base. If I'm put into a university, I'm forced to be a student. I do want to show this last one at the molecular level to show you what exactly is happening. So I'm going to draw NH3 like this. We know it's pyramidal. We know it has one lone pair of electrons on it. And then I'm going to draw water as such. So it's bent and we know it looks something like this. So if an ammonia molecule, which is dissolved in water, and it will dissolve in water because it is very polar, if it hits a water in the right orientation with enough energy, what will happen is this hydrogen will leave the electrons that is bonding it together to the oxygen behind. It will jump ship, and it will bond onto this set of lone pairs of electrons. This transition is just a proton. There's nothing else. There's no electron there. So the water is donating the proton. The ammonia is accepting the proton. And so I want to draw this similar on the other side. I'm going to leave this in black, and I'm going to leave that lone pair of electrons there. I could draw that as a line, but I'm doing this to emphasize the fact that this hydrogen that has joined the ammonia is simply a proton. It has not brought an electron with it. Because of that, the ammonia, NH4, is now positive because it has one more proton than it has electrons. Now, what's left of the water? Well, what's left of the water is this. That lone pair of electrons that was used for bonding is still there. It still has its other two pairs of electrons, and then it has this hydrogen. Now, because it has one more electron than protons, this is negatively charged and is known as hydroxide. And hydroxide is base. That is what base is. Base is a hydroxide ion. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.